I'm Cody Rue. This is the Church of Logic. And we're here at part 2 of explaining algorithms for SAT. We just explained something called the unit propagation, where Phil noted that, hey, you have a clause, one of the ands, and inside is an or, but sometimes there's only one thing, or zero things, right? Both of those cases are kind of trivial. If there's only an A in there, or only a not A, you know what to set that variable to. And by setting that variable, you learn a bunch of things about the other clauses. If A appears in another or, then that clause is satisfied, so you can just delete it. And if it appears negated in another clause, you can just delete that single A, and then you're left with a smaller big or. And sometimes that big or becomes unit itself, and now you know again what to assign there, and you can keep going. And if you're lucky, you end up with basically an empty clause, and that's SAT, right?
Yeah, eventually if it just the whole thing reduces to true and you've assigned enough of your variables, if you got really lucky, if you kept like doing this simplification process of finding units and propagating them and setting them, there's a chance you find enough, you set enough variables that you get true, and then that's your solution. And then this is actually sort of a general principle we're just talking about, like stepping back from SAT specifically for a moment. Like this is kind of what, almost exactly what you do when you're doing Sudoku is the thing that I bring up, where it's like, if you filled out an entire row except for one box, you know exactly what's in that last box. And now that keeps cascading into new rows and new diagonals and things.
Yes, that's a great example. And of course, Sudoku could be theoretically encoded into a SAT problem, but that's sort of beside the point.
Yeah.
This general idea of like finding new facts and then using those new facts to find new facts without ever kind of making some arbitrary choice of like, hey, maybe it's a 9 in this box or maybe it's a 1 in this box, right? Without guesswork, as much as you can do without guesswork is always great, right?
Yeah.
Because it avoids you making a different guess. Now, sometimes you have to guess, right? Sometimes you have, A or C, and you've done all the unit propagation you could do. You have no clause with just a single variable. And, well, you're stuck. You have to sort of make a decision. And there if you have A or C, you pick one of those two, and you try true. And you say, okay, I'm going to set this to true. And now, maybe I have a unit clause now. Or I've set it to false, and now I definitely have a unit clause, that's C. And I'm going to keep doing the propagation and stuff until I get stuck again. And then I'm going to pick a new variable, and then I'm going to set it to true or false. And then if that doesn't pan out, if I propagate all this stuff and I don't get a satisfying assignment, I basically hit bedrock where I have a clause left that can't possibly be satisfied, right? Or I've assigned all the variables basically, and I end up with something that's always going to be false. Then you go back and you try the different truth value. This unfortunately means you do have to go back and forth, and so there's still this possibility of hitting sort of an exponential case where you have to assign a bunch of variables, but you still gained a lot by doing the propagation. All right, what are the two other tricks I wanted to talk about? Yes, one brilliant trick is back jumping. So if you've picked an A and you've assigned true, and then you do all this unit propagation, then you pick you pick another variable and you assigned another truth value, and you do unit propagation, and at the end you have this kind of unsatisfiable constraint, right? You have false or false or false. You can't possibly satisfy it. What you can do is you can examine that unsatisfiable situation, and you can try to say, hey, I assigned all these variables, but that didn't matter. At the end of the day, the reason at the end that I'm unsatisfiable only depends on variables A and B and C or something. And so when you backtrack, you can go back to the last decision that actually mattered. You can skip all those decisions that didn't matter. And that's great. That saves a lot of work. And it's also kind of, it's what you want to do in real life, right? If you made a bunch of decisions and one of them turned out to, something bad happened, you don't want to try the last decision you made, right? Maybe it was, have turkey for lunch instead of ham or something. But that really didn't influence the bad thing that happened. So you want to go back to that decision, and you want to make the different decision there. This is called back jumping, right? It's sort of contrast to backtracking. And it is a very powerful idea. You can really avoid a ton of duplicated work like this. In general, this is the whole name of the game, right? You want to avoid unnecessary or duplicate work.
Mm-hmm.
And the last idea is conflict learning. Basically, if you hit a unsatisfiable situation, you want to understand why that situation occurred. Saying unsatisfiable quickly is hard. You want to understand why that situation occurred, and you want to learn how to not hit that exact situation again, or at least identify it as soon as possible to avoid going down that path. Do you have more insights on this?
I mean, I find I'm a little vague, to be perfectly honest, on exactly how you derive the conflict clause from a conflict. It's some graph algorithm. I think it's not that complicated at the end of the day, but I've never worked through the details, so like, I don't have good insight.
I'm afraid I'm in the same situation. What is true is naively you can look at all the things you've assigned, right? You've picked A, you've assigned true. You've picked B, you've assigned false. You've picked C, you've assigned true, say.
Mm-hmm.
So now you know that if A is false and B is true and C is false, then you're in this unsatisfiable situation. So you're going to negate that whole thing.
Yep.
Say either A is false or B is true or C is false. And that's a clause.
Right.
You just add it to your set of clauses. And you know you're not going to go down that exact path again because you've added a clause that's exactly the negation of that thing you've hit.
Right. So so you can make a clause. So that's a good point. That there's multiple clauses you could possibly put to decide to learn. And the one he described is the very simplest one of like, literally don't let me make the same decisions I made just now ever again.
Correct.
So like all the things that were actual branches and not just propagations, make a clause out of that, say, make the opposite decisions. Don't make exactly the decision I made at each of those points.
Right.
And if you add that now, you'll never end up back in the old position.
Yeah, the exact same position.
But the idea is you want to abstract a little bit. You want to learn a little bit more, learn something that's simpler, something that's more generic, generalizes better. So in a sense, it's kind of interesting that SAT solving at its core has something like a counterexample guided loop, which is a common technique in general. Again, I think going outside of just SAT, of like, you ask a thing something, it gives you back a counterexample. You want to generalize that counterexample using some methodology to like avoid going back into that bad spot. That's a way to like talk with solvers.
Yeah, I think part of what I think makes software smart is what makes humans smart, right? You find a mistake that you made and you vow to never make that exact same mistake. And the more clever you can be of like, this is really the underlying cause of this mistake, and I'm not going to do this again because it's going to get me in trouble. The better you are at that, the smarter you end up being. And SAT solvers are really good at a specific instance of this smartness, which is try not to make the same mistake when you're making decisions. The last bit of smartness, and then I want to share an anecdote about Daniel Kroenig and his demo. But the last bit of cleverness is, yes, I mentioned that you pick a variable when you run out of unit propagations. You need to pick a variable, and that you assign true or false to that variable, and that's the point where you'll backtrack again. The choice of that variable is like hugely important in practice. Like when you make a natural SAT problem and you want to solve it quickly, which variable you pick at each point is just going to make a huge difference. It can be like exponential to polynomial. Like the choice of that variable can really completely influence your strategy. And I think there's like a huge amount of literature on like how should you try and pick those variables. As far as I can tell, a reasonable heuristic is something called heat, where you sort of figure out how often variables end up in these unit clauses, and each time they kind of end up in a unit clause, like being important to make other decisions, you sort of say, oh, this variable is pretty hot right now, and so you bump up the heat a little bit, and then you always pick the hottest variable to make a decision on, the hottest non-assigned variable. But this is really where my knowledge breaks down. I don't remember the details.
I think if the listener wants to hear more about like more details, a survey of the state of the art, there's a really great article recently, like the Silent Revolution, I think it's called, on SAT solving and some of the heuristics that have become really powerful and important. They mention conflict-driven clause learning and other things. It's a fantastic article, and they do talk about there's some named heuristics that have been famous through the years. There's glucose. I think is glucose the same thing as heat? I'm not familiar.
Yeah, I'm not sure.
In any case, these things are refined, and heuristics really matter. And they're not heuristics in the sense that they're doing anything wrong. They're just like guiding a strict search to perform faster, a strictly correct search.
Yeah. The only thing I wanted to add to this, and then we'll kind of call it quits on SAT solving for now. Daniel Cronig, who's worked in this area for years, presented this really cool demo. And now I'm quaking a little bit because I'm afraid he'll hear, and it wasn't him that presented this example, but I hope people that listen will forgive me. Basically, he showed how to encode a list sorting problem into SAT. And it was this sort of straightforward encoding where you sort of say, hey, being at position I is some Boolean variable, or n Boolean variables where n is like the number of bits you need to know for that position, right? Like before element 3, but after element 2 or something.
Mm-hmm.
So you encode all these Boolean constraints, and then you also encode the fact that the list needs to be ordered, right? You encode, this, element at list 3 needs to be greater than element at list 2, position 2. And okay, you'd expect this to be a nightmare, right? You'd expect this not to work at all, to sort lists of even like a moderate size. You put this into the off-the-shelf solver, and it immediately sorted the list. It was instantaneous. So it's very, very non-operational encoding, right? You just say, hey, give me a list that's sorted, that has the same elements as the input list. And I'm just going to encode sorting in this sort of naive way, or encode being sorted in this naive way. And then I'm going to ask you to run the circuit backwards, right? Say I have a sorted list. It's this permutation of this input list, and just find one. And it worked. It just worked. So the point was kind of like, here's the thing you would expect to be impossible to do for an off-the-shelf SAT solver that doesn't know anything about sorting. And actually it does it instantaneously. So like SAT solvers have gotten really good. And this is kind of cool because like now you can use them to do all these sorts of search problems that you wouldn't expect to work. All right, that was kind of the survey. We ran a little long with this one, but SAT solving is such a cool field that I feel like, we'll be forgiven.
It's really exciting.